Dear students, welcome to a lecture on chemical properties of soil, pH and soil nutrient status. First of all, let me introduce the topic. Soil is the unconsolidated mineral or organic material on the immediate surface of earth and serves as a natural medium for the growth of land plants. The two essential things that plants absorb and remove from the soil are water and nutrients. Plants can be considered deficient in an essential nutrient element when there is virtually none in the soil, or else there is a large quantity in the soil but too little of it is sufficiently soluble or available to supply plant needs. As a consequence, a total chemical analysis of the soil generally reveals little information that's important for plant nutrition. Instead, it is usually a relatively small part of the total element present in the soil that is available and important for plant growth. For these reasons, the major properties of soil like cation exchange capacity, ion exchange reaction, soil pH, solubilities and biochemical transformations are related to availability of the elements present in soil. First of all, the pH. The concept of pH is based on the ion product of water. Water is neutral because the concentrations of hydrogen and hydroxyl ions are equal. pH is a symbol used as quantitative measure of hydrogen ion concentration in a given substance. Using a strict chemical definition, pH is the negative log of hydrogen ion activity in an aqueous solution. The pH value varies from 0 to 14, with pH 7 indicating that the soil has a neutral reaction. Values smaller than 7 indicate acidity and the values greater than 7 indicate alkalinity. The farther more from the neutral point, the greater is the acidity or the alkalinity. That is, lower pH value indicates a stronger acid and a higher pH value indicates a stronger base. In pH scale, each pH point multiplies acidity by a factor of 10. For example, a pH of 5 is 10 times more acid, that is, have more hydrogen ions than pH 6 and 100 times more acid than pH 7. So, a 1 unit change in the pH value signifies a 10-fold change in the actual activity of hydrogen ion, and the activity increases as the pH value decreases. Soil pH is an excellent indicator of a soil's suitability for plant growth, as it determines the availability of plant nutrients in the soil. This diagram represents the general relationship between plant nutrient availability and soil reaction. From the figure, nitrogen, phosphorus, potassium, sulfur, calcium and molybdenum are maximum available in the pH range of 6.5 to 8, while as iron, manganese, boron, copper and zinc are maximum available at the pH of 4.5 to 6.5. Now, the factors affecting the soil pH. First of all, we will discuss the role of carbonates in slightly to strongly alkaline soils. Parent materials have a wide pH range. Young soils inherit the pH of these materials. Throughout the world, however, there are many parent materials and soils that contain carbonates and are calcareous. When calcareous soil is treated with dilute hydrochloric acid, carbon dioxide is produced and escapes as a gas. Hydrolysis of carbonates produces an excess of hydroxyl relative to hydrogen ions to produce alkaline soil. The hydrolysis of calcium carbonate is sufficient to account for a pH as high as 8.3. If the soil contains sodium carbonate that is more soluble than calcium carbonate, there is greater hydrolysis and production of hydroxyl and the pH may go as high as about 10. Calcareous soils are 100% base saturated. These exchangeable bases also react with water and by hydrolysis produce hydroxyl ions. The strongly adsorbed calcium that tends to dominate the exchange surfaces hydrolyzes very little and is not very important. When exchangeable sodium saturation is 15% or more, there is sufficient hydrolysis to produce a pH as high as 10. Thus, soil is in the pH range of about 8 and up to 10 have a pH that is controlled mainly by carbonate hydrolysis. To a lesser extent, it is controlled by hydrolysis of exchangeable bases except in soils with 15% or more exchangeable sodium. Now, the role of exchangeable hydrogen and exchangeable bases in slightly acidic and alkaline soils. Mineral weathering in soils may contribute bases that accumulate as carbonates for the maintenance of carbonate system. In the absence of leaching in soil with an acidic soil moisture regime and an inheritance of carbonates from the parent material, the soil may remain calcareous and have a pH dominated by carbonate hydrolysis. Soils developing where soil moisture regimes are acidic may become leached of carbonates. In time, a point may be reached when the soil is non-calcareous and is 100% base saturated. The cation exchange capacity of these soils is commonly dominated by 2:1 clay and organic matter, and pH of about 8 is common. If the release of bases from the mineral weathering equals the loss of bases from the soil by leaching, cropping and so on, the soil may remain 100% base saturated and the pH remains above 7. If, however, the amount of water moving through the soil increases and or the release of bases from weathering decreases as primary minerals are depleted, exchangeable bases will be lost from the soil. Exchangeable hydrogen ions will begin to saturate the cation exchange capacity. Many slightly or moderately weathered soils have a pH of 7 when the hydrogen saturation is 20% and the base saturation is 80%. Such moderately weathered soils are generally dominated by silicate clay and humus ion exchange systems. Soil pH is caused by the competing effects of exchangeable hydrogen dissociation and the production of hydroxyl ions from exchangeable base hydrolysis in soil ranging from slightly alkaline to slightly acidic. As leaching continues and soil pH declines, the cation exchange capacity declines, in large part due to a reduction in a pH dependent charge of organic matter. The exchangeable hydrogen on the pH dependent sites of organic matter shows fewer tendencies to ionize as pH declines. Thus, as soil pH declines below 6, the hydrogen associated with pH dependent sites of organic matter becomes increasingly less exchangeable and increasingly more bound, and exchangeable hydrogen becomes less important as a source of soil acidity. Some organisms have a rather small tolerance to variations in pH, but other organisms can tolerate a wide pH range. Studies have shown that the actual concentrations of hydrogen ions or hydroxyl ions are not very important except under the most extreme circumstances. It is associated conditions of a certain pH value that's most important. Inherent factors affecting soil pH such as climate, mineral content and soil texture cannot be changed. Natural soil pH reflects the combined effects of soil forming factors, that is parent material, time, relief or topography, climate and organisms. The pH of newly formed soils is determined by minerals in the soil's parent material. Temperature and rainfall control leaching intensity and soil mineral weathering. In warm, humid environments, due to leaching from high amounts of rainfall, soil pH decreases over time in a process called soil acidification. In dry climates, however, soil weathering and leaching are less intense and pH can be neutral or alkaline. Soils with high clay and organic matter content are more able to resist a drop or rise in pH. That is, they have a greater buffering capacity than sandy soils. Although clay content cannot be modified, organic matter content can be changed by management. Sandy soils commonly have low organic matter content, resulting in a low buffering capacity, high rates of water percolation and infiltration, making them more vulnerable to acidification. Soil pH varies in time and space and also varies over seasons. During seasons with low to moderate rainfall, when evapotranspiration greatly exceeds precipitation, salts are not being removed by deep percolation, and increased salts tend to reduce pH by forcing more of the exchangeable hydrogen ions into the soil solution. Conversely, during wet season, salts are removed from the topsoil and pH goes up. This season to season fluctuation in total salt content should not be confused with long-term soil acidification. The most important effect of pH in the soil is on iron solubility, which in turn affects microbial and plant growth. A pH range of 6 to 6.8 is ideal for most crops because it coincides with optimum solubility of the most important plant nutrients. Some minor elements like iron and most heavy metals are more soluble at lower pH. This makes pH management important in controlling movement of heavy metals and potential groundwater contamination in soil. In acid soils, hydrogen and aluminum are the dominant exchangeable cations. The latter is soluble under acid conditions and its reactivity with water, that's hydrolysis, produce hydrogen ions. Calcium and magnesium are basic cations. As their amounts increase, the relative amount of acidic cations will decrease. Factors that affect soil pH include parent material, vegetation and climate. Some rocks and sediments produce soils that are more acidic than others. For example, quartz-rich sandstone is acidic, limestone is alkaline. Some types of vegetation, particularly conifers, produce organic acids which can contribute to lower soil pH values. In humid areas, such soils tend to become more acidic over time because rainfall washes away basic cations and replaces them with hydrogen. Addition of certain fertilizers to soil can also produce hydrogen ions. Liming the soil adds calcium, which replaces exchangeable and solution hydrogen ions and raises soil pH. Lime requirement or the amount of liming material needed to raise the soil pH to a certain level increases with cation exchange capacity. To decrease the soil pH, sulfur can be added, which produces sulfuric acid. Now the role of pyrite. In coastal areas, salt marshes occur and soils contain available iron and pyrite. These soils are flooded and water saturated most of the time. Under these reducing conditions, sulfur reducing bacteria produce sulfide. As long as soil remains flooded and reducing conditions exist, marsh plants grow well and pH may be almost neutral. However, due to lowering of the sea level or elevation of the land, the soil becomes aerated. Sulfur oxidizing bacteria may convert the sulfur within the pyrite to sulfuric acid. The pH may drop below 4, even as low as 2, and conditions can become too acidic for plants to survive. Now the role of fertilizers. Crop fertilization can also produce substantial soil acidity. Continued use of ammonia or ammonium fertilizers can lead to acidic soil conditions by the microbially mediated reactions. Nitrification of ammonium in 1 mole of ammonium nitrate results in 2 moles of nitric acid and 1 mole of sulfuric acid. Even ammonium hydroxide is acid forming. Upon nitrification, 1 mole of ammonium hydroxide produces 1 mole of nitric acid. The acidity from the nitrogenous fertilizers is not present in the fertilizers but is developed in the soil microbiological transformations of the common fertilizer material. Superphosphate is the only one that is inherently strong acid but does not have any long-term effect. Now dear students, the major changes in the soil pH. Two major groups of factors cause large changes in the soil pH. First, those resulting in increased adsorbed hydrogen and ammonium, and those which increase the content of adsorbed bases. First, the acid forming factors. In the process of organic matter decomposition, both organic and inorganic acids are formed. The most widely formed is carbonic acid, which results from the reaction of water and carbon dioxide. The solvent action of carbonic acid is evident by its dissolution of limestone or calcium carbonate. The long-time effects of this acid have been responsible for the removal of large quantities of bases by solution and leaching. Inorganic acids such as sulfuric acid and nitric acid are potent suppliers of hydrogen ion in the soil and are responsible for the development of acidic conditions in the soil. These acids are formed by organic decay processes and from the microbial action on certain fertilizer material. Leaching also encourages acidity in the soil as bases that have been replaced from the colloidal complexes or dissolved by percolating acids are removed by drainage waters. In addition, acid rain also contributes in the increase of soil acidity. Now, the base forming factors. Any process that will encourage high levels of exchangeable bases such as calcium, magnesium, potassium and sodium will contribute towards a reduction in acidity and an increase in alkalinity. Weathering process is of great significance, which releases exchangeable cations from minerals and make them available for absorption. Addition of limestone augments the supply of metallic cations. Irrigation water also frequently contain various kinds of salts whose cations are absorbed by soil colloids, thus increasing soil alkalinity. Now coming to the soil nutrient status. First of all, the nutrients present in the soil. The soil supplies the essential nutrients for proper plant growth and production. These nutrients can originate from weathered minerals or from decomposing organic matter. Now the nutrients and their plant available forms. First, primary nutrients. The first one is nitrate nitrogen in the form of nitrate, ammonium nitrogen in the form of ammonium, phosphorus in the form of dihydrogen phosphate and hydrogen phosphate, and the potassium ions. The secondary nutrients include calcium, magnesium and sulfur. The micronutrients include iron, manganese, boron, molybdenum, copper, zinc, chlorine, nickel and cobalt. For plants to be healthy, they need a steady supply of nutrients from the soil. Nitrogen, phosphorus, potassium, sulfur, calcium and magnesium are required in relatively large quantities and hence are the macronutrients. Others are required in small quantities and form the micronutrients or trace elements. The examples are copper, zinc and manganese. A shortage or absence of any one of these essential nutrients can severely retard plant growth. Too many nutrients can be as bad as too few. The availability of nutrients is affected by the pH level of the soil. For example, in very acid soil, manganese and aluminum may be present in toxic concentrations. The nutrient status of a soil can be determined by laboratory analysis of the soil or the plants that grow in it. First, nitrogen. One of the key soil nutrients is nitrogen. Plants can take up nitrogen in ammonium or nitrate form. At pH near neutral, that is 7, the microbial conversion of ammonium to nitrate, that is the nitrification, is rapid and crops generally take up nitrate. In acid soils, that is pH below 6, nitrification is slow and plants with the ability to take up ammonium may have an advantage. Soil pH also plays an important role in volatilization losses. Ammonium in the soil solution exists in equilibrium with ammonium gas. The difference between ammonia and ammonium is a hydrogen ion. For example, if ammonia were applied to a soil at pH 7, the equilibrium condition would be 99% ammonia and 1% ammonium. At pH 8, approximately 10% would exist as ammonia. The equilibrium is strongly pH dependent. This means that a fertilizer like urea is generally subjected to higher losses at higher pH. But it does not mean that losses at pH 7 will be 1% or less. The equilibrium is dynamic. As soon as a molecule of ammonia escapes the soil, a molecule of ammonium converts to ammonia to maintain the equilibrium. The important point to remember is that under conditions of low soil moisture or poor incorporation, volatilization losses can be considerable even at pH values as low as 5.5. Soil pH is also an important factor in the nitrogen nutrition of legumes. The survival and the activity of rhizobium bacteria decline with increase in soil acidity. Now the phosphorus. The form and availability of soil phosphorus is also highly pH dependent, as the kind of phosphate ion present in the soil solution varies with the soil pH. When the soil is neutral to slightly alkaline, the hydrogen phosphate ion apparently is the most common form. As the pH is lowered and the soil becomes slightly to moderately acidic, both hydrogen phosphate and dihydrogen phosphate ions prevail. At higher acidities, dihydrogen phosphate ions tend to dominate. Because of the formation of insoluble compounds, a soil reaction which yields a mixture of hydrogen phosphate and dihydrogen phosphate ions is usually preferred. As soil acidity increases, there is a rise in activity of iron, aluminum and manganese. And under such conditions, soluble phosphorus is fixed as very complex and insoluble compounds of these elements, especially when soil pH is below 5. If the pH of a mineral soil is raised much above 7, the phosphate nutrition of higher plants is disturbed in other ways. First, at higher pH values, complex insoluble calcium phosphates are formed. Furthermore, at pH values above 7, the excess calcium may hinder phosphorus absorption and utilization by plants. The type of phosphorus in aluminum phosphorus and iron phosphorus minerals under acidic conditions tends to be more permanent than in calcium phosphorus minerals. Between 6 and 7, phosphorus fixation is at a minimum and availability to higher plants is at maximum. Now potassium. The fixation of potassium and entrapment at specific sites between clay layers tend to be lower under acidic conditions. This situation is thought to be due to the presence of soluble aluminum that occupies the binding sites. Raising the pH through liming would increase fixation and reduce potassium availability. However, this is not the case, at least in short term. Liming increases potassium availability, likely through the displacement of exchangeable potassium by calcium. Now, the exchangeable calcium, magnesium and sodium. As the exchangeable calcium and magnesium are lost by leaching, the acidity of soil gradually increases. Consequently, in humid region soils, there is a fairly definite correlation between pH and the amounts of these two constituents present in the exchangeable form. In arid regions, the same general relationships hold except under conditions where a substantial amount of sodium is absorbed. Now the aluminum and the micronutrients. When pH of mineral soil is low, appreciable amount of aluminum, iron and manganese constituents are soluble, so much that they may become extremely toxic to certain plants. However, as the pH is increased, precipitation takes place and the amounts of these ions in the solution become less, with the result at neutrality some plants suffer due to lack of available manganese and iron. If soil reaction is held within a pH range of 6 to 7, the toxicity of aluminum, iron and manganese and the deficiency of iron and manganese may be avoided. Copper and zinc are affected in the same way by rise in pH. The critical point is pH between 6 and 7, and above 7 their availability declines. Molybdenum behaves counter to it. Boron is somewhat different and more complicated. Although neither the soil untreated nor the lime alone appreciably precipitate boron, the two in combination render it unavailable. Also, the excess of calcium may hinder in the movement of boron into the plant. Too much calcium in plant cells might even interfere with boron metabolism, even if plenty of boron were present. It has also been suggested that lime may create serious competition for boron by stimulation of soil microorganism activity. Now the sulfur. Sulfate sulfur, the plant available form of sulfur, is little affected by soil pH. Now we will come to the nutrient availability and the pH relationships. Perhaps the greatest general influence of pH on plant growth is its effect on the availability of nutrients. Soil pH is related to the percentage of base saturation. When the base saturation is less than 100%, an increase in pH is associated with an increase in the amount of calcium and magnesium in the soil, since they are usually the dominant exchangeable bases. Many studies have been conducted that relate increases in plant growth with increases in the percentage of calcium in plants and with increasing pH or percentage base saturation. Another nutrient whose availability is increased as the pH is increased on the low end of the pH range in soil is molybdenum. At low pH, molybdenum forms insoluble compounds with iron and it is rendered unavailable. Under these conditions, plants susceptible to molybdenum deficiency such as cauliflower, clover and stress will show a growth response to an increase in pH. The fact that increased availability of molybdenum occurs as the pH increases is responsible for molybdenum toxicity for plants in some soils. Potassium availability is usually good in neutral and alkaline soils that reflect the limited leaching of exchangeable potassium. The availability or solubility of some plant nutrients decreases with an increase in pH. Iron and manganese are two good examples. Iron and manganese are commonly deficient in calcareous soils. Phosphorus and boron also tend to be unavailable in calcareous soils that result from reactions with calcium. Phosphorus and boron also tend to be unavailable in very acidic soils. Copper and zinc have reduced availability in both highly acidic and alkaline soils. So, we can say that for the plant nutrients as a whole, good overall nutrient availability is found near pH 6 in high base status soils. The soil pH in low base status soil generally never exceeds 6 or 6.2. That's all. Thanks a lot.